Today we are going to solve the problem 3.20 of Griffith third edition, Introduction to Quantum Mechanics. Earlier I solved this problem and I have uploaded the same, which is a very lengthy mathematics, involves lengthy mathematics, and I have uploaded into two parts because it involves lengthy mathematics. Here I am going to use the less mathematics, and I am going to solve the same problem in a very simple manner without much mathematical step. So the problem 3.20 is the test the energy time uncertainty principle for the wave function in the problem 2.5 and observable x by calculating sigma h, sigma x, and time derivative of expectation value of x exactly. So we know the uncertainty, energy time uncertainty is delta E into delta T is equal to or greater than h cross over 2. We know the time derivative of expectation value of x can be written as error in measurement of x, delta x over delta t, error in measurement of t. So now you can interchange this term. Bring this to the left hand side and this to the right hand side. So you will get delta t this side. Delta t is equal to delta x divided by the time derivative of expectation value of x. So delta e I am writing as sigma x, and delta t sigma x over the modulus of time derivative of expectation value of x. Uh, this can be the second term. This ratio can be uh, ratio is defined as tau. That is the characteristic time. Characteristic time. So now we can simply write this as sigma x multiplied by the characteristic time is equal to or greater than h cross over 2. Just we will prove this with simple mathematics. From equation 2.5, psi of x and t is, that is from equation 2.5, psi of x and t is equal to 1 over square root 2 psi 1 e power minus I e1 t over h cross plus psi 2 e power minus I e2 t over h cross. This is the linear combination of ground state and first excited state. So, by definition, we know the expectation value is psi star x psi. So, if you include psi star uh, x psi, then you will get 1 over square root 2 as 1 over 2. Now you can use Dirac notation instead of integral form, which is little bit tedious in writing the equation. So inner product. So you have these two. First, you take the inner product of psi 1 with psi 1. So psi 1 with psi 1, we are taking inner product with the x. So 1 over 2 psi 1 x psi 1. Similarly, the other thing 1 over 2 psi 2 x with psi 2, that is pra vector and get vector. Next thing is psi 1 x psi 2 and this exponential term e power I e2 minus e1 t over h cross. Here that 2 got eliminated because there are two terms here. Psi 1 psi 1 x psi 2 and psi 2 x psi 1. So that 2 comes here 2 times this value. So 2 this half will get cancelled, will become 1. we have to take only the real part because the expectation value is real. Now you can rewrite this in an elegant way. 1 over 2 x11. X11 represent this. This is represented by x11, and this is x22, and this is x12 multiplied by this exponential term, where omega is equal to E2 minus E1 over H cross. So here you can see the physics part of it. Since dominant oscillation in expectation value of X is caused by this one, because here only you have a time factor. So this only oscillate. You will get it will go to maxima or minima. So a reasonable approximation is the expectation value of X as a function of time. These two we can ignore. The first two we can ignore this. So we can take that one because this is the oscillatory one. So real part of x12 e power I omega t. So this real part of x12 is because here you have imaginary number. So you can take a modulus of x12. This is the expectation value of x. So the expectation value of x is equal to real part of x12 exponential I omega t. Now, if you differentiate this, what you will get? If you differentiate this, you will get I omega. Then it is exponential term. That means it's a imaginary part. So omega multiplied by imaginary part of x12 e power I omega t. So here e power I theta, we know e power I theta is equal to cos theta plus I sin theta. Here the imaginary part is sin theta. So in our case, this will become the time derivative of uh, x expectation value of x is equal to this. Already we have seen omega is e2 minus e1 over h cross, and this is x12, the first part, modulus of x12, and this imaginary part is sine omega t plus pi. Pi is the phase factor. Now, what is tau? Tau is equal to expectation value of x over the time derivative. Of course, the modulus of time derivative, which is equal to now expectation value of x we have seen approximately equal to modulus x12. Then you divide this by time derivative of the expectation value of x, that is this one. So then the h cross go to numerator, then e2 minus e1, and you have modulus x12 uh, multiplied by sine omega t plus psi. This entire thing will come, except this h cross go to numerator. Then now you can cancel this. That is modulus x12 and modulus x12. Then we will get h cross over e1 e2 minus e1 multiplied by sine omega t plus pi. So this is the characteristic length as defined already. That is tau. Then we will find the uncertainty principle. So far, we have seen the characteristic time. Now we are going to find the sigma h. So we know the expectation value of h is equal to half E1 plus E2. We have reasonably assumed that E1 and E2 will have same probability. That is why we have seen 1 over 2. That is 50% E1 and 50% E2. Then the expectation value of h squared is equal to half e1 squared plus e2 squared. Then what is expectation value of h squared minus expectation value of h whole square, which is equal to the expectation value of h squared is of, as shown in the yellow color bond, of e1 squared plus e2 squared. Then if you square this, you will get minus uh, this one. I will use different color. This one, h cross squared is 1 over 4 because it's a 1 over 2 is here, e1 plus e2 whole square. Now you, in order to make uniformity, I am dividing and multiplying the first two term by 2. So this will become 1 over 4, 2e1 squared plus 2e2 squared. And this I am taking minus 1 over 4, a squared plus b squared plus 2ab. That is e1 squared plus e2 squared plus 2e1 e2. So now if you subtract this and this, you will get E1 squared. 1 over 4 is common. So 2 E1 squared minus E1 squared is E1 squared. Similarly, 2 E2 squared minus E2 squared is E2 squared. And minus this one, third term, 2 E1 E2, which is equal to 1 over 4 E2 minus E1 whole square. This is A squared plus B squared minus 2AB for now. So sigma x is equal to square root of this one. Expectation value of h squared minus expectation value of h whole square, which is equal to 1 over 2 e2 minus e1. So now we have to check the uncertainty principle. Now our task is to check the uncertainty principle. So as I said, sigma h multiplied by the characteristic time tau is must be equal to or greater than of h cross. So now we have seen the sigma h just now is equal to of e2 minus e1, and tau is remaining thing, this h cross over e2 minus e1 multiplied by sine omega t plus pi. Pi is the phase factor. Now you can cancel this e2 minus e1 both in the numerator and denominator. So you will get h cross over 2 1 over sine omega t plus pi. So you know very well the value of sine theta varies from 0 to 1. So at the maximum value, you will get just h cross by over 2. If it is less than 1, then the 1 over sine omega t increases above 1. So which is always higher than h cross over 2. So the maximum value of h cross over 2, that is sigma h multiplied by tau is h cross over 2. When this value sine omega t over pi is 1. Otherwise, this will be more than h cross over 2. So thank you very much for watching my video and supporting me continuously. Thank you very much.